Radiation patterns from antennas are formed by electromagnetic waves leaving the metal antenna elements. But these radiation patterns do not automatically carry information that we can use to communicate. Instead, sound, numbers, or other information to be communicated must first be encoded by a modulator inside a radio before transmission, transmitted in an encoded format, then received and decoded by a demodulator in the radio at the receiving end. A modulator works by converting information like spoken language or Morse code into something that modifies the antenna's carrier signal before it leaves the transmitting antenna. This modified signal carries the encoded information. There are 4 basic ways to encode digital information: amplitude modulation, frequency modulation, phase modulation, and a combination of amplitude and phase modulation known as Quadrature amplitude modulation. Let's think about these 4 methods by using the Morse code for SOS as an example. Amplitude modulation changes the height of each wave, depending on whether a dot or a dash is encoded. For example, every time a dot is sent using amplitude modulation, the carrier wave's amplitude decreases by half, and every time a dash is sent, the carrier wave's amplitude increases by 2. To do this, first the modulator converts the dots and dashes into a new signal. This new signal is represented by the black square wave above the dots and dashes. A lower line corresponds to a dot, and a higher line corresponds to a dash. This new SOS signal is combined with the default carrier wave signal that the antenna usually sends. When the 2 signals combine, there are changes in the amplitude of the wave transmitted by the antenna. Since everything else about the wave stays the same, the result is an AM radio signal, AM for amplitude modulated. Frequency modulation works similarly to amplitude modulation, but instead of changing the height of each wave, there is a change in the wave's frequency, which is how quickly the waves are sent. So when a dot is encoded using frequency modulation, more waves are sent in 1 second, and when a dash is encoded, fewer waves are sent in 1 second. To do this, the modulator converts the dots and dashes to a new signal, then the new signal is combined with the default antenna signal. However, this time when the signals are combined, the wave fluctuations change in certain places to modify the frequency of the wave. Since only the frequency is changed to convey information, the result is an FM radio signal, FM for frequency modulated. Phase modulation is slightly different from amplitude and frequency modulation. First, it is important to understand that the phase of a wave determines where in the wave cycle a signal is at a given time. At the beginning of a wave cycle, the phase is 0 degrees. Halfway through a wave cycle, the phase is 180 degrees. And at the end of a wave, the phase is 359 degrees before starting over at 0 degrees. Similar to reading directions on a compass or hours on a clock. When a modulator uses phase modulation, the dots and dashes are encoded in the carrier signal by jumping to certain wave phases in the default signal. So to encode our SOS signal using phase modulation, each dot could be encoded as a wave jump to phase 90 degrees, and each dash as a wave jump to phase 270 degrees. When the modulator in the radio outputs the signal, the amplitude and frequency stay the same, but since the SOS is encoded in the phase, the line of the wave looks jumpy in places. Finally, Quadrature amplitude modulation, also known as QAM, combines amplitude modulation with phase modulation. This is important because it allows for more symbols to be encoded than when amplitude or phase modulation are used alone. There are also many other modulation methods, each with different advantages depending on the application and context. And each method can be further altered to enhance the accuracy or efficiency of a transmission. For example, one way the accuracy of modulated signals is enhanced is by increasing the error detection and correction of a signal. Using our SOS message as an example, the operators of the transmitter and receiver could agree in advance that each dot or dash in the SOS will be transmitted 3 times. This way, even if the transmitted message signal encounters interference, like the radio waves given off by power lines, and some of the letters in the SOS are lost before it reaches the receiver, there is a better chance that the receiver will be able to understand the whole message. If the signal is received perfectly, the receiver knows to only consider one of the 3 repeated signals. So whether there is signal loss due to interference or not, the message is understood correctly.